Okay, so we're going to start part 3 of 11.10, and we're going to start with our exercises where we were left with the sine and the cosine functions, and we wanted to compute their Taylor series. And it's going to be true that sine of x, and we're not going to show it formally, is going to actually equal its Taylor series. And it's actually going to be true for all x. We'll see that in a little bit. And we're going to be centered at a equals 0, which is our so-called Maclaurin series. So let's compute some derivatives. The procedure for all of these, whenever you're doing it from scratch, is first take basically a bunch of derivatives, try to see if there's a pattern, and then construct your series. So here I'm just writing down some derivatives of the sine function. So we have f of 0 is 0, f prime of 0 is 1, f double prime is 0, f triple prime is negative 1, the fourth derivative is 0, and you'll see this pattern continuing. So it'll be 0, 1, 0, negative 1, 0, and then back to 1, 0, negative 1, and then again 0, and so on. So our Taylor series for this function is f of 0, which is 0, plus 1 times x minus 0 divided by 1 factorial, plus 0 times x minus 0 squared over 2 factorial, plus, well, I guess I should have a minus sign because we're having a minus 1 there, minus 1 times x minus 0 cubed over 3 factorial, and so on and so forth. So you can see that all the even order terms are going to go to 0, only the odd terms survive. So you actually get just x minus x cubed over 3 factorial. The next term that survives will have a positive 1 coefficient, and it'll be odd, so you'll have a plus 1 times x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. So we can compactly write this in the following way. Negative 1 to the, well, let me first write the x power, x to the 2n plus 1 over 2n plus 1 factorial, because remember 2n plus 1 is always an odd number, and I want this to start at n equals 0. So this is the Taylor series of sine of x, and this is actually, so sine of x, and this is the part which we're not proving. We're not showing the remainder, whole remainder thing. We're just going to assume that it works out, which it does. And hence we have this. And the question is now, where is this true? It'll be true wherever this converges, wherever this series converges. So we have to find out where this series converges, and then we'll be done with this part. So we again use the ratio test to find the interval of convergence. So we're going to have the limit as n goes to infinity of the n plus 1th term. And remember, with the absolute value sign, I don't have to worry about the negative 1s here. I'll have x to the, if I replace n with n plus 1, I have 2n plus 1 plus 1 over 2n plus 1 plus 1 factorial times 2n plus 1 factorial divided by x to the 2n plus 1. And of course, we want this to be less than 1. Well, what do we get here? This is 2n plus 3 and divided by 2n plus 1. So we have x to 2n plus 3 divided by x to the 2n plus 1 times 2n plus 1 factorial divided by 2n plus 3 factorial. And we have our limit. Well, what is this? We're only left with just 2 powers of x, so we have absolute value of x squared, and then times the limit, because effectively we're testing this out for each fixed x value. This will become 1 over 2n plus 3 times 2n plus 2. And then everything else will cancel with the 2n plus 1 factorial. So all that's left is this. Well, when n goes to infinity, this equals 0 for each x value, right? So no matter what finite x value you put in, that actually equals 0, and that's less than 1 for all x, right? So this is less than 1 for all x. So hence this series converges everywhere. Hence this series converges for all x. And so we have then that sine of x is actually equal to negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, so that's sine of x. Let's go ahead and proceed. So this is on the whole real line. Let's go ahead and let's try a different color here. Let's try cosine of x. See how that goes. Well, for cosine of x, we're again centering at 0. F prime is negative sine. F double prime is negative cosine. F triple prime is sine. And again, once we get to the fourth derivative, we get back to cosine. So we have f of 0 being 1, f prime of 0 being 0. F double prime is minus 1. Triple prime is 0. Fourth derivative is 1. So we have this, again, repeating pattern, which if you keep going, you get 0, minus 1, 0, and so on. In this case, only the even terms survive. So our Taylor series for this particular function is 1 plus 0 times x minus 0. Oops. Minus 1 times x minus 0 squared over 2 factorial plus 0x minus 0 cubed over 3 factorial plus 1 times x minus 0 to the 4th over 4 factorial, and so on and so forth. So what do we get out of this? We get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and it'll continue this pattern that all the even terms are the only ones that survive. So how do we write this in compact notation? Well, we'll have something that's alternating again. And here, though, instead of 2n plus 1, we want just 2n because we want even numbers. And then starts at 0, goes to infinity. And I'm going to leave you to check. So it turns out, so the cosine of x is actually equal to this series, x to the 2n over 2n factorial. And by a very similar argument, so I'll leave this as a little exercise you can show. So exercise and I'm not going to do this exercise, I'm just going to leave it for you, show that the interval of convergence I is everything. It's very similar to the previous one for the sine function. You just use the ratio test. So use ratio test. Okay, so that concludes those two problems. We have now quite a list of Taylor series that we have derived between 11.9 and 11.10. So I'm just going to write these down because it is kind of important to know these. They can come up quite often in differential equations and various other places. So let's see, here we have negative 1 to the n, this is 2n plus 1 over 2n plus 1 factorial. We had this, then just now we saw the cosine function was negative 1 to the n, x to the 2n over 2n factorial. From one of the previous sections, we derived the formula for the tangent inverse, and this was one where we did it with some integration, and we had negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Note that there's no factorial here, and this this was the series expansion. By the way, this converges for all x. This is also for all x, for both of these. This one was not for all x. This was, the radius of convergence was 1 here. And you can check the interval of convergence here, I believe was, let's see, if we plug in negative 1, just have a negative 1 times this. Plug in positive 1, so this is actually the closed interval here. And then we also did the ln of 1 plus x, which was negative 1 to the n, x to the n plus 1 over n plus 1. And here also r was 1, where the actual interval, if you plug in 1, you get an alternating series, but if you plug in negative 1, you don't get an alternating series. So you're open at negative 1 and closed at 1. So these are kind of some of the series that we've seen so far. Notice that all of these are centered at 0. So what I want to conclude this section with is an example where we're not centered at 0. So we're going to do an example here of computing a Taylor series. So let f of x be 1 over x. And let's say we're centered at a equals 1. And we want to find, instead of finding the whole Taylor series, maybe I'll leave you to do that. Let's find, say, the third order Taylor approximation, which is f of 1 plus f prime of 1 x minus 1 plus f double prime of 1 x minus 1 squared over 2 factorial, and then the third order term x minus 1 cubed over 3 factorial. So this is the third order Taylor approximation. I'm not finding the whole Taylor series. There may be a problem in the homework that deals with that if I'm not mistaken. So, well, let's just compute these. So we want f of, well, first of all, let's compute some derivatives. So this is d by dx of x to the minus 1. So this is minus 1 x to the minus 2. F double prime is the derivative of that. So we get minus 1 minus 2 x to the minus 3. And f triple prime is minus 1 times minus 2 times minus 3 x to the minus 4. And you might ask, why am I not simplifying these? Well, when you want to find the whole Taylor series, we want to see the patterns. And it helps not to simplify these in order to see the patterns. So for example, this is negative 1 cubed times 3 factorial x to the minus 4. And first of all, well, after we do this, we have to plug in the numbers 1. So let's do that just below here. So f of 1 we already know is 1 over 1, which is 1. F prime of 1 is minus 1. F double prime of 1 is minus 1 squared times 2 factorial, which is 2. And the third derivative at 1 is minus 1 cubed times 3 factorial, which is minus 3 factorial, or minus 6. So what do we end up with? Our third order Taylor approximation is 1 minus 1 times x minus 1 plus 2 times x minus 1 squared over 2 factorial minus 6 x minus 1 cubed over 3 factorial. So what we end up with is 1 minus x minus 1 plus x minus 1 squared, because the 2's cancel. Here 3 factorial is equal to 6, you get minus x minus 1 cubed. So this is the third order Taylor approximation of for f of x equals 1 over x. And you can fairly easily generalize this to its Taylor series if you'd like to. Okay, that concludes 11.10. We will begin the next section, next video.